because for this curved beam, for the curved members, and the members here means the structure, okay, structure beam. The structure can be a beam, can be a rod, can be a column, this kind of thing. So this is a curved beam. We talk about the curved beam and how to calculate the stress because the neutral axis and this is the centroidal axis for the curved beam, and they are not a coincident. They are not the same animal, so we need to differentiate. This is a natural axis or natural line. This is a central axis or central line. And here is a deflection. We talk about the deflection and how to this is. You can see if we have a contributed force, and so because this guy for any given is a theta angle, and we can decompose this I into I theta and I r, and definitely we have a bending moment here. So all these I r, I theta, and I am along with this I theta, because this I theta, when we decompose this I into I theta and I r, the point of entry or the point here we move to the centroidal line. Okay, centroidal line, that means it is different from the neutral axis. As a result, this I theta itself will generate a bending moment. The magnitude is I theta multiplied by the E. So E is the distance between the centroidal line and the natural line. So you should know that. We can see very clearly. Usually this is the centroidal point and the neutral point is here. So this force is going to bend this beam this way, which is opposite to this end. As a result, in the equation to the straight energy, we have a negative sign here. So be very, very careful. Okay. Why we have a minus sign? Because this bending moment, because due to this I theta. That is opposite with the bending moment, and this is resulting from this error on this point. So you can see if this is our U and screen under this is screen for the whole beam, right? For the whole beam, and then we can use the Castigliano theorem. So this Castigliano theorem is a derivative of U with respect to F. The whole derivative of the whole scale energy with respect to the corresponding F equals the displacement of this corresponding F at this given point. So we are going to use this equation. So generally for any thick circular curved member with a proper limit of integration, so we have this integration. We are going to have an example. So for specific example in figure for this one. And this I'm theta, I'm theta, r, and they are given here. All this is and these are given in this column, and these four are given in this column. And we are going to use these these variables here based on this equation to calculate the problems. So this is the substitute, and you can just substitute and the factorial. And you will have this delta equals this, and finally, so this is the delta can be written in using these three terms. So you can see this is a minus sign. Don't be surprised. Why this is a minus sign? I told you guys already. Right? Questions? So you can see even any delta, you want to get this is this I given the applied I and how to calculate deflection, and using this equation, you can see all this is unknown I. And E, Young's modulus, A is area cross-sectional area, and E is the distance between the neutral axis and the centroidal axis. R is the radius of the central line. So this is a C. This is the C is because of the transverse shape. It is dependent upon the cross-sectional area. And we will keep. Questions? So using this equation for this specific problem, delta is calculated using these three terms. Questions? No question? Then we are going to, what if is that we have a thin curved beam. If a thin curved beam means that here, okay, a thin curved beam, and we mean that thickness of the beam is very, very small. We use usually R divided by H. the H is thickness, we use H is thickness. If the ratio of U and to the H is greater than 10, so this is the E. In physics, this is the E is very small. And so in this case, and the U can be, this is the string energy can be written approximately using this one. You can see if the same beam, for the same beam, so only the bending moment is dominant. All other three, this is a conclusion from this you can see here. So this one, I would say this one and this one, and these three, they are negligible. This is negligible if this is the beam is very thin. So only this one is dominant. That's the reason. So this delta for thin beam and this deflection can be approximated using this equation instead of using these terms. Questions? No question? No question. We have one example here. And so this example, so here is the beam, this is the beam, and then here is a circle, a half circle. And so this is center this is the center of this half circle. We have a concentrated force P, and this geometry is given. This is L and this R, and we are asked to calculate the deflection at the point D, right? The deflection at the point D, if we have a concentrated force, the P, and this is the middle of this is a half arc. So how to calculate this one? So definitely this is a curved beam. So this is a curved beam. So what we need to do is that we need to use the Castigliano's theorem, right? We need to use Castigliano's theorem. Castigliano's, how can we use the Castigliano's theorem? So you need to know that look at this beam. This is a structure. This structure is composed of, so this is a straight line. It's a straight line here. And so this is, and this half arc, whenever we see a concentrated force, we always differentiate this beam, dividing this beam at this point into two parts, right? Because the concentrated force usually generates, this is a singularity. So here, this is the segment 1. So from here to here is segment 2, and from here to here is segment 3, right? So the segment 3. So we have, this is the U, and this is delta, right? Delta equals, and this is a du and df. So we have 3 segments. Segment 1, segment 2, and from here to here is a segment 3. And also, we are asked to calculate the deflection at point D, right? But we can see at point D there is no force. What should we do now? We use a fictitious force. We use a fictitious force. That means we draw. I cannot draw on the screen. Okay, so we draw. This is the dotted force. We draw Q. Okay, we draw Q. So this Q is applied at the P dotted. That means that it's a fictitious. And then, so this equation, the delta is supposed to be written as du and dq. Then our task is to calculate the u, right? To calculate the u. And how to calculate the u? So also guys, and here, right? So this is r equals 50. Here r equals 50, and the diameter equals 20. Is a 2, and 50 over 2. Equals the 50 over 2 equals 25 is much greater than 10. Okay, so this is the R, and so this is the D. So this is the same beam, and this is the same beam, and we only take care of the moment, take care of the contribution of the moment, and which means that this is as we said here, this delta equals du and df, and we only use this equals 1 over ei. So this is m and dm and df r d theta. So the same beam, because it is the same beam. The same beam. And we only use this equation. So we only use the contribution of the bending moment m. So all other the contribution from other terms we just ignore. Make sense? Now, if you for our case, and for our case here, the delta equals du dq, right? And du dq, and then we just plug in f over ei, so m and dm and dq r theta. And so the similar problem will appear in our exam 1 for this problem, right? So I want you guys fully understand and how to do it, the thinking process. So M, dm, dq. Now, as I told you guys, this beam is composed of 3 segments: segment 1, segment 2, and segment 3. And why I just divided this one into 2 segments? Because, as I said, concentrated force is always a troublemaker, right? And so whenever you see the concentrated force, you always just divide the structure at this given point, because you are going to write something differently for this part and for that part. Make sense? Whenever you see the concentrated force, you must divide the structure at that point where you apply the concentrated force. Okay? No question? But let's look at this. And this one, okay, this is U. Okay, this is U. As I said, we have 3 flat segments. So this is U, and then this is delta equals and D U1, U2, U3, and then divided by Q. Right? So U1 is the straight underneath for this segment. U2 is the straight underneath for this segment, and U3 is the straight underneath for this segment. Do you guys agree? So I just you can this equals du1 dq and plus and du2 dq and plus and du3 and dq. Okay, right? And then we look at the first one. And for the first segment, how to calculate this is for the first segment. For the segment 1, for segment 1, and so this is my segment. And this is the segment. So this is the so I use here as a this is the origin. So this is the x. So this x. And so here, okay, so here still. So what I want to calculate is that, so here is the MTA, MAB, right? So for any generic point x, and this here is the MAB, and this bending moment, and also we have, and this is a VAB, V is a transverse shear. You guys agree? So this is a transverse shear force along with the bending moment, and these two guys, and they are going to balance the force and moment generated from the right hand side. Right? For the right hand side, we have a P here. So this is the actual force. And also we have a Q here. So this is a fictitious force. You guys agree? So I know for this point X, generic point X, now this is my origin. This is my X, right? So I know, so this point, it is in the state of equilibrium. Right? Because it does not translate, it does not rotate. But then I can know that this MAB must be balanced by the bending moment generated from P and from Q. You agree? And then I can write this MAB and equals the P and multiplied by this guy's effective arm from this point at which this guy is applied and to this point X, which equals this X and plus the radius of the this arm. And then I have the Q, and even though the Q even the Q is fictitious, but I need to take the derivative with respect to this guy. So I need to write down and Q multiplied by this guy's effective arm and from X, which equals X and plus this R and plus this R 2R. Right? And then this is MAB, this is for the first one, for first segment. And first you can see for the first segment, I need to have M, I need to have dm dq. So then I have this M already, then I calculate and dmAB and dq. So this one has nothing to do with Q. So only the second term is related to Q. So I know the derivative of this guy with respect to Q equals X plus 2R. Okay? That works? Okay, I would say I call this one as delta 1, and this one as delta 2, and this one as delta 3. Then the delta 1, okay, the delta, yes, it's 1, I'm sorry. And then the delta 1 equals, and du1 and dq equals, and u1, okay, so this is u1, and this is the u. The du1 dq is this one. And so du1 dq, we will have ei, okay? This is ei. Then this is the m1. M1 I use MAB to stand to denote. MAB. Then and dm1 and dq, dmAB and dq. And then I have R. Then I have R d theta. But we don't have this is dx. This is a so this is dx, okay? For if the straight line, if it's a dx, and either r theta or because now we are this is a straight line which is a dx. This is a dx. So we have this is a dx, and then we have this integration. is a dx. I'm only talking about this from here to here. So this is like for segment 1. And so you can just plug in this MAB, just plug in, and now the Q equals 0. MAB is a Q equals 0. And so you can just have this 1 over EI. And so from 0 to L. Okay, so this is from 0 to L. And then we have MAB, so it's a P x plus R. Px plus R. Okay, so this is Q equals 0 because we know the Q equals 0. Q equals 0. And then we have this one, x plus 2R and dx. You just plug in, and so you can calculate. And so the first one. So this we call delta 1. Delta 1 means the contribution from the first segment. So why we have the dr, this r theta? This is for the curve. This is for curve. If it is a straight line, so this is a dx. You can see physically r d theta. That if it is a curve, it is still the dx. It's still the increment for here. From here to here, this is an increment. But now this is a straight line, so that's the reason we use dx. Questions for the first one? No question. And we look at for segment 2. For segment 2, the segment 2 is this. And we also here, and we just use this theta is from 0. This is 0 and to 90 degree. From theta to 0, rotate to 90 degree. So this is a free body diagram. And we can see, so we will have MPC bending moment, and we will have NBC, the central, and we will have a shear, the stress, the shear, this is a stress on VPC. Now, if we just take a look at this curve, and we do the free body diagram, we have a P here, and we have a Q here. Now for this one, we know this is half is also in the state of equilibrium, and so MPC, NPC, VPC, and they are balancing these two. This is external forces. One is the P, one is Q, even though the Q is fictitious. You understand? And then we can just calculate based on the moment balancing equation. MAB equals the bending moment generated by P and plus the bending moment generated by Q. So this is on how we calculate, and this is the M and BC. MBC equals the P, T, the P is here. So this is my the point of interest. The effective distance between the P and point of interest is from here to here. The length of this straight line, right? Which equals the radius multiplied by sin theta. You guys agree? I go. You agree? Okay. So let me repeat. Okay. So this P is here. This is my point of interest. The effective arm of this P with respect to this point equals, I got draw a line from here to here. This is a straight line, which equals the R multiplied by sin theta. So this is my effective arm. So P multiplied by this guy's effective arm R sin theta. R sin theta. Then plus the contribution of Q, and this Q is here. So this guy, the effective arm of this Q is from here to a horizontal line, which interacts with at this point. And the length of this one equals this part, r equals r multiplied sin theta plus another r. So that is the q is r plus r sin theta. So this is MPC, and then we take a look at the DMPC over Q. And so once again, so this term has nothing to do with the Q, and we only have this one, which equals R plus R sin theta. And then we just plug in this equation. So keep in mind now we have R d theta now. So because it's a curve, this is a curve. So the delta 2 and delta 2 equals 1 over EI. So MBC multiplied by DMBC and DQ. And then R and d theta. Now this time it is for my left arm, so this arm, which equal this theta is from 0 and to half pi. From 0 and to half pi. And then you just plug in and the E over I just take them out, and from 0 to half pi MBC. So also and Q equals 0. We know that Q equals 0, so this one will not have any contribution. We just have, this is P R sin theta, and then multiply by DMBC dq, which equals R plus R sin theta, parentheses, another parenthesis, and then D and d theta. And then you can just calculate. So, questions regarding this one? Okay. Okay. Eden. Okay. I'm memorizing your names. Your name is Michael, right?
Wait.
Huh?
Clayton.
Clayton. Okay, I'm sorry.
Yeah.
Michael, that guy's name. Okay. Good.
Yeah. Could you just explain one more time the formula at the top of segment 2? Why we incorporate sine, or how we generate the
This one.
yeah.
This one. Okay. So let me draw here. So here is a generic theta. Okay. So I'm look at this is the point. This is the point of interest. So I know this point is in the state of equilibrium, right? So I know if I have MBC, this MBC is balanced by the P and by Q, right? And then you can see the P is going vertically down. So if I draw a horizontal line, so this one, this guy will be the effective arm of this force. Do you agree?
Yes.
So the P multiplied by itself is the effective arm to the point that is the moment the P generates. Right? The same thing for here. If I for the P for the Q, I just vertically extend it here. Also here, I just vertically extend it. So this is the whole thing will be equal to R sin theta plus another R.
Gotcha.
Okay, so this is another R. Thank you very much for this question. Questions? No question? Let's look at the segment 3. The segment 3 is for segment 3. For segment 3 here, you can see this is a pre-board diagram, and still we have the theta. Okay, the theta is from this is 0 minus 0 theta, and to this is the theta. This theta equals half pi. And so this is any general point, this is of interest, in this case, angle is theta. So we have MBD, okay? So MBD is balanced by the Q. You guys agree? And I'm CD, I'm sorry, I'm CD. CD is balanced by Q. CD equals what, guys? CD, this is my point of interest. So the Q, if I draw a vertical line here, let's see here. So this is my curve. This is the theta. So I'm interested in this point. So this is my Q. So this is my MCD. Right? And then the Q, what is the effective arm? The effective arm of Q with respect to this point, it equals to this, right? You guys agree? It equals this. So this equals the whole R, the R minus the R cosine theta. This is also R. R cosine theta equals this. Right? So R cosine theta. So that means, so this is so MCD equals Q R minus R cosine theta. You guys agree? And then DMCD DQ and equals R minus R cosine theta. Then you just plug in. You just plug in, and we have this is delta 3, and delta 3 equals also from 0 to half pi. And so this 1 over EI. So MCD is MCD, right? And multiplied by DMCD EQ and R and cosine theta. Now, so this is very, very beautiful, okay? So this is, remember, P equals 0. Now, you can see MCD here, I don't have any other term. I only have one term. This guy Q equals 0. That means, and so this is delta 3 will be equal to 0. Because MCD equals 0 if Q equals 0. This one equals 0. Right? You guys agree? So I just want to tell you guys, just follow this procedure, and finally this equals 0. So then finally, the delta equals delta 1 plus delta 2 plus delta 3, and you can calculate it. So as I said, a very similar problem will appear in our exam 1. I want you guys to calculate, right? So let's summarize what we have learned from this one. For this one, because this curve we cannot use one equation and to accommodate all these geometry. So that's the reason we need to divide this guy into several segments. Right? That's the reason. For example, if we use R and theta to describe this curve and this curve, and how can you use R theta to describe this one? It's impossible, right? That's the reason we just carve it here. So this is my first segment, and then, as I said, is whenever you see the contributor force, always carve it at that point. That's the reason we have this one and we have this one. So our assumption is that because at the very beginning we know the ratio of R to the D is 25. That means this beam is very, very thin, very slender beam. As a result, and our delta, okay, only dominated by the movement, bending moment. That's the reason we can just ignore other two terms. You understand? And that's our assumption, okay? So that is our analysis, the reason why we just ignore other terms. Because for this so thin the beam, only the bending moment is dominant. So based on here, and we know this equation, so you can see the U, okay? The U equals the total speed energy equals the speed energy of the segment 1 plus the speed energy of segment 2 and so on and so forth. And as a result, this one can be written this way, and it can be written as dU1 dQ, U2 dQ, and U3 dQ. Then we have these three guys that we then finally we sum them together. Then we go through each of these segments and using the moment balance equation, because we only have moment here. Using the moment balance equation, we express the bending moment at any generic point x. And then we just plug in here. Also get this is the derivative of m, which is here. Then plug in. And then we do the integration. We go through all these segments. Questions? If I change the geometry of this one or change the load, you should be able to give me an answer, right? If you know this or what we have done, here. But this here is important. Some students, based on my teaching experience, previous teaching experience, some students just ask me, Tolma, and why you just use the bending moment? What about the contribution of other terms? So here is this is the reason. Okay? This is the reason. Because it is very thin, very slender beam. If I do not have these kind of things, so this kind of geometry do not give you the geometry information here, I'm supposedly I usually use all the terms. That's another story. You can see NBC, VBC, and you need, if this is not a thin beam, and you need to calculate NBC and VBC also. How to calculate it? And just use the force balance equation. But here we only use the moment balance equation, right? Because only bending moment is dominant. And we just ignore the contribution of NBC and VBC. That makes sense? Okay, good. Yeah, that is for this one. We still have some time. Let's move on to next slide. Next one. So this is deflection. Also, actually, this is the overlapping of today's we have talked about. This is 5, the chapter 5. We have talked about this one. And then we move on new things. So here is an example, the deflecting in a variable cross section, the punch stress the frame. So here, so for this one, this example I will not take a look, but I want you guys to know that. So here is a punch. So this is on how to do this. You can just take a look. Okay, this is a delta. How to calculate the delta using deflection if we apply the Pound force here. So keep in mind, is a cross-sectional area of this beam, they are changing, right? And they are changing. And this is analytical solution. I will not take a look. You can just take a look. But what I want you to do is that, and you use IVM and to do it. Right? So this is the analytical solution, and then I want you to use IVM to build the model. And because the symmetry, guys, because of symmetry of this structure, and we only take care of the top one. That means I just cut it here. That's the reason we only use this kind of geometry. So here is a boundary because the symmetry, we have another half, the symmetry, and the displacement of all these points in this direction equals 0. Okay? Because this guy is symmetric. So that means all these guys displacement in vertical direction equals 0. And this is the boundary, and then you apply a load, and then you submit this job to the system, and then the system will solve the problem. and then you can compare your FEM results with analytical results. Questions so far? So now this time, this is not a thin beam. You need to be very careful. And then we talk about the compression members. Compression members means we just compress the structure. The column, a member loaded in a compression such that either its length or eccentric loading causes it to appearance more than pure compression. Either its length or eccentric loading. Eccentric loading means that the loading condition is not along your centroidal axis. That's called eccentric loading. So there are different kinds of columns. These are length. That means if the length is very, very high and it buckles, and this is buckling. I'm talking about buckling here. So the four categories of columns: long columns with the central loading. Central loading means that the loading direction is along the centroidal line. That means there is no eccentric loading, but it's very long, so the buckling occurs. Second one is intermediate length column with the central loading. This is central loading. So column with eccentric loading. That is eccentric loading. That means in addition to the force along the centroidal, also there is a bending moment because of the eccentricity. The struts or short columns with eccentric loading. So this is the four conditions we usually see in our reality. So first one, we talk about long columns. The columns you can treat it, you can understand them as the beams or whatever. That's the beam or the column or the kind of member. So you can see. So this is a P. When P reaches a critical load, right? Critical load. So I just say critical load. I did not say how to calculate critical load. The column becomes unstable and bending develops rapidly. So critical load depends on the end conditions. So this is our form commonly used the central loading. So this is C, okay? So we have four cases. Four cases. On the C for C equals 1. And so these two ends, they are pinned. Yes? You know pinned, right? Pinned means that this guy cannot translate, but this guy can rotate. You can see it can rotate. Right? So this one C equals 4. And so here is a fixed. Fixed means that both translational degrees of freedom and also the rotational degrees of freedom, they are fixed. But here is also fixed. And for this case, C equals 4. And the C, what is C I'm going to talk about? Right? C equals 1/2. That means one end is fixed. And now another end is open. And C equals 2. One end is fixed. Another end is pinned. So we totally have 4 different cases. So these are different cases. What's the C? And C is a value, okay? For pinned, okay? For pin-ended column, first one. For pin-ended column, the critical load is given by the Euler column formula. So PCR equals pi square EI L square. L is the total length. What? So I'm talking about buckling. Now this is a failure, this is critical, does not mean that this is a material yields. I'm talking about the buckles. As long as the structure buckles, I think it fails. Buckling is horrible in reality, in industry. You understand, right? So you can see, so this PI is proportional to the Young's modulus and also the area moment of inertia. That means geometry of the cross-section area. However, it is inversely proportional to the length. That means the longer your arm is, the lower the PR will be. What? and then apply to other ends, and we can have a C here. So this is very outstanding exceptional equation. So for other cases, the PR can be calculated using this same equation for the pin-ended column, but and we can add a C here. Is time now? Yes. Okay, so I'm going to stop here now. Okay, so I hope you have a wonderful weekend.
Thank you.
Right?
Thanks, Dr. Moore.
Okay, so this afternoon I'm going to give another homework, okay? Okay.